Okay, so now we've got to chapter 7, more on conditional probability. And obviously this chapter focuses on partitions and how you can use conditional probability to work out um, probabilities of events in which the sample space is partitioned. So we've got our three theorems and definitions. I'll quickly whiz through them. 7 point. I'm not going to prove any of them actually. The only one I kind of show is the extension of 7.3, 7.1, and 7.2. The reason why I'm not proving them is because they're very easy to prove, and the proofs in the notes, and it's very it's clear as day in terms of how they're proved. So there's not really a point of me doing that. So yeah, let's just quickly whiz through this and then go on straight to an example, because I feel like the best way to really sort of get these ideas in your head is through an example. So obviously definition of partition, the events E1, E2 all the way to En. Partition, sample space or form partition if they are pairwise disjoint, i.e. Ej intersection Ek is equal to the empty set for all j not equal to k, and the union is the whole of the sample space, i.e. E1 union E2 union all the way to En is the sample space. So basically what we're saying is we've got a pizza and cut into n slices, and the union of each slice is the pizza, and the pizzas don't overlap. So obviously, like, if you get a pizza delivered, well, assuming they're a half decent company, you get the slices not overlapping each other, which is basically the intersections being the empty set, right? Obviously they'll be touching, but they don't necessarily intersect. So yeah, that's basically it. I'm sure you understand what partition is. I'm just doing that to be extra. So right, we've got theorem 7.1, which is total probability theorem. So that's if E1, E2 all the way to En partitions the sample space, and the probability of EI is not equal to 0 for all I. Then for any event A, we have the probability of A is a sum from I equals 1 to N of the probability of A given EI times probability of EI. Obviously, we'll apply these theorems, so I will go through them when applied, but I'm just making sure that you can everything's readable. Now we've got theorem 7.2. If E1, E2 again, all the way to En again, if it partitions a sample space and A and B are events with the probability of B intersection EI greater than 0 for all I, and then we have A given B is a sum from I equals 1 to N of probability of A given B intersection EI times probability of EI given B, right? And then we have 7.3, which is Bayes' theorem. So for any events A and B, the probability of those events A, B are greater than 0. We have B given A is the probability of B, A given B times probability of B over probability A. And here we have this extension of the formula. And just as a quick note, if you wanted to know how they got this, well, the numerators are the same, so that's no different. But the probability of A, well, by 7.1, we can apply the probability of A is equal to this, right? So if I set E1 to B and E2 to B complement, right? So now let me just have that as a better B. So yeah, E1 equals B and E2 equals B complement. Well, then this is going to go from I equals 1 to 2, because obviously N is 2. The partition is just 2 pieces. And it's going to be the probability of A given E1 times E1 plus probability of A given E2 times probability of E2. So, which is illustrated here. And obviously E1, if you replace all the E1s with Bs, because obviously E1 is equal to B, and you replace all the E2s with B complement, you'll see that that mirrors that. And so we can substitute that in. So that's just a quick, brief explanation of how they got that. Which can be quite useful, because obviously depending on what your scenario is, you may need to jump to this formula. So yeah, depending on what they give you. Right, let's go into an example. So a box contains 2 fair coins and 1 unfair coin with 2 heads. A coin is selected at random from the box and tossed twice. What is the probability that both tosses show heads? If both tosses show heads, what is the probability that it is the unfair coin? Okay, so let's see. So let's say, do they partition? Well, we've got 3 coins and a coin is selected at random and tossed twice, right? So 1 is selected out of the 3. So I'm going to let E1, equal F1, meaning the first fair coin. E2 is going to equal F2, the second fair coin, and I'm going to let E3 equal F subscript C for the bias coin. Right? I don't want to write F complement because it's not actually the complement of anything in this question. But obviously I'm going to write F subscript C just to make it clear that this is the biased coin, or the coin that's not fair, right? So obviously these these are distinct, right? So assuming that the coins are distinct, you have the first fair coin and the second fair coin, right? So what do we want? We want the probability. Well, the first question was, what is the probability that both tosses show heads? Because obviously the coin is tossed twice. So we want the probability of H1. So, and H1, I haven't defined H1. So H1 is going to be the event that obviously the first toss is heads. Well, what's that going to be? Well, by 7.1, our total probability theorem, well, my A is going to be H1. See, H1's A now. And it's going to be the sum from I equals 1 to 3, because obviously I've got E1, E2, E3, and it's going to be this. It's going to be probability of A given E1 times E1, and the same for E2, same for E3. So probability of H1 by applying 7.1 is going to be the probability of H1 given F1 times probability of F1 plus the probability of H1 given F2 times the probability of F2 plus the probability of H1 given FC times by the probability of FC. Hopefully that's clear. That's just H1 given FC times by FC. I'll just try to squeeze that in. Probably should have started a new line. Well, what's this going to be? So we'll probably have H1 given F1. So that's probably of the first coin is heads, given that you got the coin that you tossed was the first fair coin. Well, if the coin's fair, it's just going to be a half. There's no debate about that. Times by the probability that the coin is fair, or the first coin. Sorry, times by the probability that you actually get the first coin, right? So, well, F1, well, there's three possibilities. There's three coins to pick from. F1 is one of them, 1 out of 3. Okay, so that's the first fair coin. Now we go on to this. So we've got plus. So probability of H1 given given that you pick the second fair coin. Well, that's going to be, again, if the coin's fair, it's going to be a half. And the probability of picking the second fair coin, well, there's only one coin. There's only one second fair coin. And so that's going to be times by out of 3 is going to be 1/3, because obviously you've got 3 to pick from: F1, F1, F2, and FC. And so probably again F2 is 1 out of 3, right? So yeah, apologies I've been really pedantic in this video, or really really bogging everything down, but this has been said to be a really difficult chapter, so I really want to make things crystal clear, even the most trivial things. I'm just going to do it. So yeah, and now we've got probability of H1 given that we've got the bias coin. Well, the bias coin, right, or the unfair coin. What did we say about the unfair coin? The unfair coin, it had 2 heads, right? So probability of getting heads, given that you've got the bias coin, well, it's going to be the certain event 1, because obviously both sides got heads. Times probability that you actually get the unbiased coin in the first place, well, that's 1 out of 3, just like all of these. So it's going to be times by 1 out of 3. So you simplify this, that would be 1 out of 6 plus 1 out of 6, that's 2 out of 6, which is 1/3, plus a third, so that is going to be 2/3, right? So now we need to get to the what else do we need to get? We need to get we want the probability that both tosses show head. So now we need H2 given H1, right? And then we go in, then we need to find from there we need to find H2 intersection H1. So that's the ultimate goal, to find H2 intersection H1. That the first coin is heads and the second coin is heads. But obviously by conditional probability, you'll see that if you want H2 intersection H1, that's going to be the probability of H2 given H1 times the probability of H1. So we've already got H1, now we want H2 given H1. I probably should have said that at the start as my sort of game plan of how we're going to actually solve this, but that's what we want. We want H2 intersection H1. So now we're going to have to solve H2 given H1. So obviously, because by conditional probability, that's what we're going to have to do if we want to find out what H2 intersection H1 is. Well, what's this going to be? Well, by 7.2, that's partly the way why I did this first, actually, because each of these steps apply each of the theorems, which is quite neat. So by theorem 7.2, if these partition, and A and B are events with probability of B intersection EI being greater than 0 for all I, then, well, we've got this. A given B is a sum from I equals 1 to n of probability of A given B intersection EI times by EI given B, right? Well, our EIs, well, we've got E1, E2, E3, just like we did before. Well, what's our B? Well, our B is now H1, because now we want the probability of H2 given H1. So our B is H1, and our A has now become H2. So by this, by applying theorem 7.2, what are we going to have? Well, it's going to be the sum from, again, it's going to be I equals 1 to 3, because, we've got E1, E2, E3. It's going to be the probability of H2 given H1 intersection F1 times by the probability of F1 given H1 plus the probability of H2 given H1 intersection F2 times the probability, I really need to stop trying to fit these in, times the probability of F2 given H1. That is not clear at all. Let me just write that out again. Times the probability of, what's this? Times probability of, that's it, F2 given H1. And I want to add this on to, apologies for the sort of lack of order here, but I have to fit that on, plus the probability of H2 given H1 intersection FC times the probability of, did I say FC or HC? FC, I meant to say, but in case I said HC, so times probability of FC given H1, right? So what's this going to be? Well, H2, so this is probably that we get, the second one is heads, given that the first one is heads and it's fair. Well, it's completely irrelevant what happened in the first scenario, because if you toss a coin, then you toss the coin the second time, what you get the second time has nothing to do with what you got the first time. So this is just the same as the probability of just getting heads. So again, it's going to be a half. And what we times by the probability of getting the first fair coin, given that you got a heads. Well, what's that going to be? Well, on a separate page quickly, the probability of F1 given H1 is going to be probability of F1 intersection H1 over the probability of H1, right? So what's the probability that you got a fair coin and you get a heads? Well, that's going to be a half times a half, so a quarter. And the probability that you get a heads, we worked that out from part 1, that was 2/3. So simplifying this down, you should get that. Oh, sorry, my bad. This isn't a quarter. Apologies. The first fair coin is not a quarter because the probability of getting the first fair coin, well, that's 1 out of 3. And the probability of getting a head, so it's going to be 1 out of 3 times 1 out of 2, which is 1 out of 6. Apologies for that. Let me see, it's nearly 5 a.m., so that's the excuse I'm just going to use. So it's 1 over 6 divided by 2 over 3, which simplifies to, let's see, what's that? So 3 over 6 divided by 2. I'm losing my mind. Yeah, 1/4. Yeah, that's 1/4. I wrote the answer prematurely. Apologies for that. So this is 1/4. So we can go back to our scenario now. So this is going to be times 1/4. Right, now we want H2 given H1 intersection F2. Well, again, like before, if you're tossing the coin the second time, it doesn't matter what happened the first time, whether it was biased, unbiased, whatever. If you toss a coin the second time, it's not related to what happened the first time. So again, that is a half. Right, because obviously the first one was fair, and yeah, it's just a half. Times by, what we got times by? Well, the probability of that you got the second fair coin, given that it's given that you got a head. Well, that's going to be the same. It's going to be the same thing as the first coin, right? Because it's got the same properties. We're just going to have F2 here instead. It's still going to be 1 out of 6 divided by 2/3. So that's also going to be a quarter. And now we've got the last one. So that's the probability of getting a heads given that it was given that you got a heads, given that the first one was a heads and it was the unfair coin, right? FC. So you're tossing the unfair coin now. So what's that going to be? Well, you're tossing the unfair coin, and the unfair coin you were certain to get heads no matter what. So again, if you're tossing a second coin and it's unfair, well, that's going to be 1 also. So obviously the unfair coin has heads on both sides, right? And so we're timesing by the probability of that it's the unfair coin given that you got a heads. So now we need to find out probability of the unfair coin given that you got a heads. Well, let's see if it's any different. So we want this given that you got a head. Since the answer isn't immediately obvious, we have to apply the conditional probability definition of conditional probability. So let's see, over probability of H1, I'm just doing this to double check. So yeah, this is going to be a third. Okay, so the probability of, what's it? Lost my train of thought. Yeah, the probability of the unfair coin and it's a head, right? Well, probability of unfair coin is 1 out of 3. Probability of it being a head and it was an unfair coin, well, that's going to be 1 out of 3 times 1, isn't it? Because obviously the unfair coin was certain to be heads. So that's 1/3 times 1 over the probability of heads. Well, that was 2/3. So we've got 1/3 divided by 2/3. The 3's cancel out, so we get a half. So this is a half. Hopefully everything is clear. There's just a lot of working out, and I have to go at a certain pace so that it's going to be a very long video. Oh my goodness. It's already 19 minutes already, but I want to go at such a pace that it's a lot of working out, but hopefully everything's clear. Right. So when you simplify this is an 1/8 plus an 1/8 plus a half. So that's going to be what's that? 4/8. I think that's 4/8. Let's see. Well, an 1/8 plus an 1/8 is, or an 1/8 plus an 1/8 is a quarter, plus the a half is going to be 3/4, right? So that's going to be 3/4, 6/8. My apologies. Right. So hopefully that's clear, right? So now we can go on to find what we actually wanted to find, which was the probability of the second one being heads and the first one being heads. Well, by definition of conditional probability, that's going to be, if you rearrange it, that's going to be probability of H to given H1 times the probability of H1. So obviously this is the same as H2 intersection H1 divided by H1, and then a times it by another H1, so the H1 cancels out, so it's the same as this. But we actually know what this is. We know what this is because we got it from just a minute ago. That was 3/4, and we know what this is. This was 2/3. And so the 3 cancels out, you're left with 2/4, which is the same as 1/2. So the answer is 1/2, and that's what you should get. That is the answer. This is exercise like 7.1 on his lecture notes, I think. It's not something you went through in the lecture notes. It's just an exercise for us to do. Right. So now we have the second question, right? If both tosses show heads, what is the probability that it is the unfair coin? Okay, so what do we want now? So now that we want the probability that if both tosses show heads, it's the unfair coin. Okay, so we've got a slightly different scenario here, but it follows the same principles. So we want the probability that it's the unfair coin, i.e. FC, given that both tosses, i.e. this, showed heads. Well, by 7.3 Bayes' theorem, B given A is the same as A given B times B over A. So FC given H1, H2, well, that's the same as the probability of H1 intersection H2 given FC, which is the bias coin, times the probability of FC divided by the probability of H1 intersection H2. Just to clarify here, our B is FC and our A is H1 intersection H2, and hopefully you can see how this comes about, how this comes about using 7.3. Okay, so this is much easier to compute because we know some of these already. Well, what's the probability of getting the first one being heads and the second one being heads, given that you tossed the bias coin? Well, the bias coin is always going to get heads, so that's going to be 1 times by let's see. Well, the probability that it was the bias coin. Well, there's 1 out of 3 possibilities, so there's 1 out of 3 chance that you actually pick it, over the probability of H1 and H2. Well, we already got that from part 1. That was 1/2. So now we have 1/3 over 1/2. Take the 2 to the top, you get 2/3. Okay, so that is an example of applying each of the theorems. That's particularly why I showed that example. I went in that order because it goes through, first of all, it requires a definition of partition, and then it goes through 7.1, it applies 7.2, and it applies 7.3. So that is an also awesome example by Valdi. But yeah, so that is how you do it. I'll probably or most definitely go through another application of Bayes' theorem, like another scenario. Examples are hard to find, but I'll find something. Just to practice. Really, with chapter 7, you just got to practice the definitions and practice the scenarios. Practice, deriving what they've actually told you and stuff. Not getting it confused, like I mentioned in the conditional probability video. Not getting, A given B, B given A the wrong way around, which is easy to when they put you in scenario-based questions and they sound very similar. But that is it. That is it. I will have more examples, hopefully, for chapter 7. I'll also have examples on using chapter three's propositions, corollaries, axioms for uh, using those to prove results that contain conditional probability within them, because people seem to sort of underestimate how key the axioms of Kolmogorov's axioms are. They're actually very, very powerful, and they come up all the time. Um, and you can easily forget it. But if they ask you to prove a result, you're gonna have to, from going from step one to step two. You cannot just jump steps. You're gonna have to say how you get it, like kind of like algebra. Like you have to prove it very, very carefully by each of the axioms. Similarly, probability, he ain't gonna let you get away with just proving some, just jumping steps for no reason. You're gonna have to show by axiom this or by corollary this. And so I'll have a video on that as well. I've got a couple of questions already stocked up for that. So that will definitely be a video that'll be making that I'll make, hopefully. So yeah, besides that, next video will be some example questions on what I just said, applying chapter 3 to conditional probability. Um, and I'll hopefully have a video on another example video of applying the theorems from chapter 7, and then we'll go on to chapter 8, which is an overlap with statistics. And I'll probably look to just really finish the module really soon, so I can move on to introduction to statistics, which just seems to be in everyone's eyes just terrible. So yeah, hopefully I'll do that, and that will be next. So yeah, obviously if there's any mistakes, which I'm very likely to make because it was a 26-minute straight video. I'm tired. This is recorded now it's about 6 a.m. in the morning. So yeah, not that it's an excuse, but hey, it's my excuse. So, hey. But if there's any errors, please let me know, and I'll just I can fix them. It's greatly appreciated when you let me know if there's something wrong, or if there's something that wasn't clear, or if there's any examples of any particular thing in probability that you want. Ask me. I'll go get some more, and I'll put videos on that. But as for now, obviously my plan is to do what I said I was going to do. So yeah, thanks for listening.